On the Zoom videos, I did talk about the second part of chapter 20, which is kinetics. So I'll just go through here, but you can take a look at some example problems on the videos. But so far, we've just been talking about kinetics from an empirical perspective, just based on the observations, what's the rate law. But in the second part, we're going to look at it from more theoretical perspective, that is based on the mechanism, that is, how these things react, what is the rate law. And so when we're thinking about kinetics, for a reaction to occur, there has to be a collision. And these collisions are actually pretty fast. How many collisions are there? So these are different numbers here from collision theory: 10 to the minus 10, 10 to the minus 13, 10 to the 32nd, 10 to the 6, 10 to the minus 4. What are those? Well, these are numbers like how many collisions are there per second, or what's the distance it moves in between. Normally, when we think about collisions, we want to know how frequently are the collisions, how many collisions occur in a second. And it turns out, it depends on the concentration. But if we're looking at your typical standard concentrations, the number of collisions, which one would you think would be the number of collisions per second?
A really big one.
Yeah, it's really big, and because there are a lot of collisions. Right. And then some of these other numbers. Some of these other numbers will refer to, and you don't need to know the other numbers, but some of the other numbers refer to things like what is the average distance traveled, let's say in meters, before things collide. And so let's track a molecule. If you track a molecule, how far does it travel typically before it hits something? And so that's called the mean free path. And so when we're thinking about collisions, we think mean free path is how long it travels before it hits something. It doesn't travel very far before it hits something. But in terms of, things that are at that scale, it's actually quite a long distance, because gases are mostly empty space, but gases are extremely tiny particles and that kind of stuff. And so, but for us, the main things we're going to worry about are, is there enough energy in that collision? Number one. And two, does it have the right orientation? And so in collision theory, the two main concerns are orientation and energy. Orientation is this probability, what's the probability of it? Like, for example, this top collision is favorable here because it has the correct orientation, but these bottom two are unfavorable, and these bottom two aren't going to result in a reaction. And so orientation and energy. Energy, it turns out there's got to be some minimum energy required to break the bonds and form new bonds. Actually, it's not in sequence. That is, you don't break the bonds and then form new bonds. It happens at once. So as the new bond is forming here, that is the NO bond, the other NO bond is breaking. And so we have NN, that O bond is breaking, this ON bond is forming at the same time, and then we end up with the products. And that amount of energy that's required to do that is called the activation energy. And the activation energy is given by this line here. Any molecule in this population that has an energy greater than this line has enough energy to react. It doesn't mean that it has the correct orientation, but it does have the correct energy to react.
How does that line determine?
The stronger the bonds, the further right it is. The weaker the bonds, the further left it is. So, for example, I was in the homework, we were talking about cooking food. When you cook foods, you don't completely break the covalent bonds. You usually break the hydrogen bonding interactions and other things, a whole protein molecules together. And so things like food would have very low or lower activation energies. And things like graphite, converting graphite to diamonds would have extremely high activation, so high that the population is negligible that can accomplish that. And so what are typical single bonds are around 400 kilojoules per mole, typically 300, 400, 500. Well, 500 is getting a little high, but 300 to 400 kilojoules per mole for single bonds. And then we're doing bond formation. Bond formation releases energy, so typical, activation energies might be around that range. Food, is less than 100, maybe in the 50 range for the activation energy. So this is what gave the rule. The rule of thumb that I learned when I was doing kinetics is for every 10 degrees C temperature increase, the reaction rate doubles. But that's only for low activation energies. For higher activation energies, that's not the case. So when we're trying to figure out the activation energy, what we're doing is we're forming this thing's called the transition state. The transition state is we have a bond breaking, the NO bond breaking, and the ON bond is forming. And so it's going to require a certain amount of energy. That certain amount of energy is called the activation energy. In this case, the activation energy is 209 kilojoules per mole. 209 kilojoules per mole is less than the energy of an NO bond. And the reason it's less than the energy of the NO bond is because we're also having bond formation occurring. Now, this transition state is a transitory state. It's not going to be something that you can isolate and study. And so all you do is you measure this using spectroscopy, shining light there, and then you can see what's happening with electrons. But what we can do is we can study the products. So in getting from the reactants to the products, it looks like you have this collision that undergoes this transition state and then drops to products. Even though the net is exothermic, we have this positive endothermic thing here. And in fact, all of these collisions will have some endothermic component, whether the net is exothermic or whether the net is endothermic. If it's endothermic, then we have an even bigger hill up to go to get the products. All right, this is what we call a simple collision or an elementary process. In a simple collision or elementary process, then there's nothing hidden in the rate. When we have a typical reaction, we don't know if it's a simple process or a more complicated process. And so when we're looking at this reaction, this is N2O. N2O plus NO goes to N2 plus NO2. We don't know if this reaction happens in one step. If this reaction happens in one step, we call it a simple process, or if it happens in multiple steps. If this reaction happens in multiple steps, then it's not an elementary process. It's not a simple collision. But we don't know that just by looking at this. But we can assume that it is, or we can assume that it isn't. And so normally you're told if it's an elementary process or a simple collision. In this case, we're told this just happens in one step when we're done. Here you can see the spectroscopy method is used. This reaction happens at the femtosecond, 10 to the minus 15 second time scale. And so it's very quick, and then it's over. So in order to study this transition state, you need something that's faster than femtosecond, to be able to see this. If you have something that's slower, femtosecond is 10 to the minus 15 seconds, but if you have something slower like nanosecond, you'll completely miss this. That is, you'll just see the reactants and then you'll see the products. It happens so fast. So basically, if we model the Maxwell-Boltzmann curve, and then we have the activation energy, we come up with an equation like this. This equation is going to be for the rate constant. The rate constant is going to equal A. A depends on the collision frequency and the probability of having the correct orientation. And so if the collision frequency is low and the probability of having the correct orientation is low, then this A is going to be small. If it's high, then A is going to be big, which means you're going to have faster reaction. So A is called the pre-exponential constant or the frequency factor. It just depends on those. And so usually you can determine the A experimentally. You can also try to determine it theoretically, but that's a bigger challenge. Then this is E to the minus EA. EA is the activation energy, the cutoff. So large activation energies, slow reaction. Small activation energies, fast reaction. And then RT, large temperatures, fast reaction. Small temperatures, slow reaction. So K, this is the Arrhenius equation. There are different forms of the Arrhenius equation here that we can look at. And so this is one form of the Arrhenius equation. The other form is to take the natural log of both sides. So if we take the natural log of K, this is going to equal E minus EA over R. This is a constant, and then the variable would be 1 over T, the temperature, plus ln of A. All right. From the second form there, this is the y equals mx plus b form. We can come up with the Arrhenius plot. And so this is the Arrhenius plot. You just measure the rate constant at different temperatures, and then you take the natural log of the rate constant, and then you can come up with the Arrhenius plot here. And so measuring the rate constant at different temperatures. From the Arrhenius plot, we get the activation energy. The activation energy is equal to the slope is equal to minus EA over R, which means the activation energy is just equal to the slope times R, and the negative of that. Okay, so in this case, they got the slope, which is negative 1.2 times 10 to the minus 4, or 10 to the positive 4. Okay, and then we figure out the activation energy by multiplying by R and dividing by negative 1. Okay, there's one more form of the Arrhenius equation, and that is if we only have 2 data points, we don't want to make a graph like that. If we only have 2 data points, then we can get this form, which is we'll take ln of K2 minus K1 at temperature 2 and temperature 1. And then we'll subtract those and we'll generate this equation. That is the natural log of K2 over K1 is equal to minus EA over R, 1 over T2 minus 1 over T1. So in the homework Zoom, I go through the derivation of this equation. This is also equal to, the rate is inversely proportional to the time. So if we have the time, it doesn't matter if it's a half-life or whatever, it's just the time of reaction. And so we can take T1 over T2. The faster the rate, the shorter the time. The slower the rate, the longer the time. So it's inversely proportional. So we get T1 over T2. This is just going to equal minus EA over R, 1 over T2 minus 1 over T1. And so these are two common equations. So if we're given one rate at one temperature, and we know the activation energy, we can figure out the other rate. So what happens? Is the rate double? Is the rate triple? We can figure it out. Or if we measure 2 rates at 2 different temperatures, we can figure out the activation energy. That's just getting 2 points. If we only have 2 data points on our Arrhenius curve, then we can get the slope easily. In fact, we don't have to get the slope. We'll just use this equation here to figure it out. We're not going to plot it, in other words. If you have more than 2 data points, then it's better to do an Arrhenius plot like this, because with an Arrhenius plot like this, you can do a linear least squares fit, which is going to average all the experimental data. There. So more than 2 data points, do Arrhenius plot. If you only have 2 data points, then you might as well use this form of the Arrhenius equation to do the calculation. So in the homework, let's go through using this. This is by far the most common form of the Arrhenius equation. All right, so what we're going to do, this is still somewhat empirical, slash a little bit theoretical, because the equation, the Arrhenius equation, does come from the Maxwell-Boltzmann thermal energy distribution and the activation energy. But what we're going to look at next is reaction mechanisms. So here's the combustion of methane. This is just a snippet of some of the reactions that are involved in the combustion of methane. And so you have all different kinds of species here on the way to CO2. This is not the complete mechanism. What they call mechanism is you just map it out. What are all of these are simple collisions, what we call elementary processes. And turns out there are a lot more. So one of them, you can look, the first thing from the top, we got methane, and we go to this, that's called a methyl radical. And then we form all these other species in here. Okay, over here, we have different elementary processes that can occur. The first one is just unimolecular. If we have a unimolecular collision, how can you have a unimolecular collision? There's only one particle. Well, a unimolecular collision can occur when that one particle hits the wall of the container, or it hits an inert gas molecule. So this room's filled with nitrogen, so maybe the A particle hits a nitrogen molecule. It doesn't react, but it causes energy to be transferred. That is, kinetic energy is converted into what we call potential energy, and that can cause reaction to occur. And so a unimolecular process is just going to be a simple collision. So the more A we have, let's say we double the number of A particles, we're going to double the rate of the reaction. Because you're going to have twice as many, you'll have twice as many collisions. We could have bimolecular, and these are 2 different types of bimolecular. It could be an A colliding with an A, so we have 2 A's colliding. So if we have the right A or the left A, from your perspective, colliding with the right A, if we double the left A, then that should double the number of collisions. But if we double the left A, we're also doubling the right A because we just have A in there. And so what's going to happen is it's going to quadruple the number of collisions, and so it's going to be second order in A. It's going to be first order in the first A, and first order in the second A, and second overall in A. Does that make sense? So that would be a simple collision. Maybe with this second one, or bimolecular, it might make more sense. So we have an A colliding with a B. If we double the A here, we're going to get twice as many collisions, which will result in twice the rate. If we double the B here, we'll get twice as many collisions. So one thing, when we have a simple process, there's nothing hidden here. If there's nothing hidden, then the coefficient comes into play. And so the rate for a simple collision or elementary process is equal to K A to the little a, B to the little b, dot, dot, dot. So if we double A, that is, if we need 2 A's, then it's going to depend on the right A and the left A, or whatever you want to do in terms of orientation. And so it'll be second order. If we only have 1 A, then it'll be first order, etc. And so by far, unimolecular and bimolecular processes are the most common. Termolecular processes are a lot less common because having 3 molecules collide with the correct energy and the correct orientation has very low probability. And so termolecular are low probability, but it could happen. And it's just going to be based on the coefficient. So this is 3A goes to product, so it's going to be third order in A. This is 2A plus a B goes to product, so it's going to be second order in A, first order in B. And this is A, B, C goes to product, and so first order in each of those. So it's an elementary. Elementary process would just be one of these humps here. So this is a two-step process here in this particular reaction. And so we don't know. The only thing is we have to label this as an elementary process or a simple collision here. And if we label this, then we know there's only one step. But in general, we can't do that. In general, if we have a reaction, we don't know if it's one step or multiple steps. So if I had AA plus BB plus ... goes to product, I don't know how many steps there are. How many steps? So if I look at the combustion of methane, I mean, combustion of methane, you would think it's just one step. Methane plus two O2s goes to CO2 and two waters, but it's not. It's very complicated. And if there are many steps here, we don't know which one of those steps is the bottleneck. The bottleneck would be the slowest step, which is called the rate determining step. And the rate determining step dictates the speed of the reaction. So the speed of the reaction might not depend on the first collision or the second collision. It could depend on the 15th collision. And whatever that 15th collision is that's going to be the bottleneck, and that's going to dictate how fast this reaction goes. So in general, we don't know, and therefore, in general, the rate is equal to Ka to the m, B to the n. And m and n come from the mechanism, the slowest step in the mechanism. That's where m and n come from. This is from the mechanism, the RDS in the mechanism. Sometimes it's we have to do some algebra to figure it out. So it could be multiple steps or it could be a single step. When I look at this reaction here, we're going to use, is this a single step? Maybe. If it's a single step, then it's a termolecular. We have to have an H2 colliding with two ICLs in the exact same instant of time with the correct energy and the correct orientation. And so, in other words, we can't have let's say the H2 is in the middle. We can't have one ICL hit and then the second ICL hit. Basically, if the H2 is in the middle, both ICLs have to hit it at exactly the same time. In other words, it has to be coordinated. A coordinated attack, like at time zero, boom. How probable is that? You know, do the two ICLs communicate with each other to say, okay, at this instant, we're going to collide with the H2 and react? No. And so this is going to be low probability. When the experimentally determined rate is determined, it's found to be this. First order in H2, first order in ICL. Could it be possible that this happens in a single step? No, it's not possible. Because when we look at the rate of reaction only requires one H2 and one ICL, not two ICLs. And so in other words, it's going to be first order in H2 and first order in ICL. So only one ICL is involved in the collision, not both ICLs coming in and coordinating the attack at the same time. So what we think about is this. We think about, okay, what can happen in this? So we might try to come up with a mechanism. And the mechanism is just kind of a guess, but it's not just some random guess. We want to do a mechanism that seems plausible, that is reasonable. So if I have an H2 and ICl collide, that's a bimolecular collision. That's plausible. That's totally reasonable. What do you think might form? If an H2 and ICl collide, what do you think might form? Yeah, HCl and HI. That's totally reasonable, right? Hydrogen chloride and hydrogen iodide, or hydrochloric acid and hydroiodic acid. So reasonable, right? But the problem is HI is not a product. You see that? And so that's what we call an intermediate product. Well, the intermediate product has to react in a subsequent step. So maybe the HI reacts with we need two ICLs, so maybe the second ICL comes in the second collision here. And so the HI collides with the ICL to form what? What seems like a reasonable... Yeah, it seems reasonable that we form an HCl and an I2. Okay, then when we combine these two steps, so this will be step 1, this will be step 2. When we combine these, the HI cancels. And so what we end up with is H2 plus 2 ICLs yields 2 HCl's and an I2. And so this is a plausible mechanism. Plausible mechanism, the net reaction has to agree with the given reaction there. And so the net reaction from my mechanism agrees. And then the rate has to agree. And so what I could do is I could just call this one the slow step. If I call the first step, and this is me assigning, I could call the second step slow, but if I call the second step slow, it wouldn't work. If I call the first step slow, that is, and then the second step fast, all it has to be, then the first step is the bottleneck, and the first step can dictate how fast this reaction occurs. It doesn't matter what's going on with the second step as long as it's faster. And so, it can only go as fast as the slowest step. So if you're stuck behind, let's say a slow moving vehicle like a tractor or something, you're not going to move any faster no matter how fast you can travel. And so here, the rate of this slow step, now both of these are simple collisions. And both of these would be simple bimolecular collisions. And so the rate of the slow step is called the RDS, rate determining step, and that's just equal to K1. We'll call this K1. H2 ICl. H2 ICl. Let me write it up here. K1 times H2 times ICl. Now, it's going to depend on one H2 colliding with one ICl. If I double the number of H2s, I'm going to double the rate. So it's first order in H2. And if I double the number of ICLs, I double the number of collisions, which doubles the rate. It's first order in ICl. And so two things here. When the rate law derived from the mechanism agrees with the experimental rate law and the net reaction agrees, then we say that this is a plausible mechanism. Plausible means this. It means that this could be one of multiple routes to products, or this could be the mechanism, or this might not be the mechanism. It's just plausible. This could work. Right? There could be more steps. There could be other branches. And so we could think of other possibilities, but once we have a plausible mechanism, then we're good with this. How can we determine if this is the mechanism? Well, transition states we can't really see unless we have like a femtosecond laser to monitor it, but intermediates we can. So we can try to detect the presence of HI. HI lives a lot longer than femtoseconds. And so if we can determine that HI is indeed in that mix during the reaction, then that gives strong evidence that this is the mechanism for the the reaction. So in order to determine whether a plausible mechanism is the mechanism, we need further study. Okay, looking at this here, the slow step is going to have the biggest hill to climb. And so if we have H2 and two ICLs, we'll have an H2 react with one ICL. When the H2 reacts with one ICL, we're going to make a transition state. The transition state for this is going to be something like this, where we have the HH bond breaking, ICL bond breaking, and the HI bond forming, and the HCl bond forming. So this would be the transition state here. That would be at the top of the peak, and that would require a certain amount of energy called the activation energy to achieve. And so the transition state would be here, that transitory state that we can't really isolate. And this would be the activation energy for step one. The activation energy for step one is going to be a lot bigger than the activation energy for step two. So climbing the first hill here is going to be the slowest. After the first hill, the second hill is a lot easier. And therefore, the first hill is going to dictate the rate. Both steps are exothermic here. Looks like it's good. All right. This is a mechanism. This is a two-step mechanism. The first step is slow. The other type of mechanism we're going to have is a two or more step mechanism where the second step is slow. So let's take a look at this reaction here. This is also, I go through in the homework a little bit. But this is 2NO plus O2 goes to 2NO2. Now, the rate of the reaction from experiment, experiment is fact. And so whatever theory we come up with has to agree with experimental observations. And so the rate of this reaction determined from experiment is second order in NO and first order in O2. Well, if it's second order in NO and first order in O2, then maybe this is a simple termomolecular collision. If it's a simple termomolecular collision, then that makes sense because it would depend on, let's say the O2's in the middle, and it depends on one NO coming in from the left and one NO coming in from the right in a coordinated collision. But, if it is termomolecular, we would expect the rate to be somewhat slow. We would expect the rate to be slow because the probability of a termomolecular collision is very low. And so the rate should be fairly slow. However, from experiment, the rate of this is fast. This happens very quickly. That is, whenever NO, which is a colorless gas, is formed, it's automatically converted in air into NO2, which is a brown-orange gas. Based on the speed of this reaction, it's likely not a one-step termomolecular collision. That would be highly improbable. It's much more likely that it's a multi-step that just has this form. And so we just take some guesses as to what forms. What's more common? What's more common would be a unimolecular or bimolecular. In this case, which one do you want to do, a unimolecular or bimolecular? A unimolecular would be like an NO colliding with the wall and breaking up into nitrogen and oxygen. Do you think that seems reasonable? Or an oxygen molecule hitting the wall. When an oxygen molecule hits the wall, do you think it's going to break up into two oxygen atoms? Probably not, No, for oxygen, definitely not. I mean, there's oxygen hitting the walls right now. And so most likely it's going to be bimolecular. Now, if it's a bimolecular, we have two choices. An NO and an NO come together, or an NO and an O2 come together. Those are two choices that we have. So we could try them, maybe both we could try. Let's say an NO comes together with an NO. What do you think forms if two NOs come together? We could form NO2 and N. It'd be atomic nitrogen. Atomic nitrogen, which would be very reactive. Or what? Maybe N2O and an O, which would be atomic oxygen, which would be very reactive. Or maybe an N2O2. N2O2. Does N2O2 exist? Dinitrogen dioxide. Well, one thing is we could try to draw the Lewis structure for N2O2. We try to draw the Lewis structure, the least electronegatives go in the center. So we get something like this, and then we try to complete the octets, the oxygens first. So nitrogen's 5 times 2 is 10, oxygen 6 times 2 is 12, so it's 22 electrons. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons. That'll be 22 electrons there. But we don't have an octet to nitrogen, so what we'll do is we'll take one off there, take one off there. Now we have an octet to the nitrogen. All the formal charges are 0. So this structure looks good. We have an octet, all the formal charges are 0. Does this look like a reasonable Lewis structure? Yeah, so also we could look and see, does dinitrogen dioxide exist? We kind of expect it to exist. Based on the Lewis structure there, it should exist. It has a common name. Dinitrogen dioxide is called dioxohydrazine. Dioxohydrazine. The IUPAC name, which would be its formal name, is N-oxonitrous amide. That is one bizarre name. Let's see about stability. If they have any other information about this. It looks like there's a lot of studies on dinitrogen dioxide. Okay, this doesn't show much for that. And so out of these three choices here, which one do you think seems to be the most stable product out of these three? The first two? Out of the first two, I wouldn't say the first two. Out of the first two, which one's more stable? Having a nitrogen radical or an oxygen radical? Which one wants electrons more, nitrogen or oxygen? Oxygen. So I'd say this one's more stable than this one. So the first two aren't equivalent. Having a nitrogen radical would probably be better than an oxygen radical. Oxygen radical would be very reactive. But these are free radicals. These free radicals are highly reactive versus N2O2, we have octets. We don't have an octet on nitrogen, nor do we have an octet on oxygen. It wants an octet, and so it's going to take electrons from something to get that octet. And so which one I think is most stable is this one. It has an octet, all the formal charges are 0, and there's studies on this, experimental studies. So for sure, this one would be the one I would go with. And so doing this one, I get NO gas plus NO gas yields N2O2 gas. Okay, now N2O2 is not one of our products, so what we're going to do is go N2O2 plus an O2, because we had two NOs and an O2, so the O2 must react in this step here, and that's going to form two NO2s here, because we're going to get N2O4, but N2O4, if we try to draw the Lewis structure, isn't going to be right, and so we'll have to break it up into two NO2s. Does that make sense? I could try to draw the Lewis structure, but I'm not.
Is there a reason why we even suggest N2 and then O2 separately as a possibility? I mean, I'm sure there is, but like, what would be the reason?
Yeah, that's also stable as well. N2 plus O2. We could do that, but N2 and O2 form a very stable mixture, air. And does air react in the next step to form nitrogen dioxide? And so the problem with forming N2 and O2, it's such a stable mixture that I'm not going to get any further reaction, because NO2 is a brown-orange gas, which is fairly toxic. And so trying the next step with this with another O2 is not going to do anything. So I kind of eliminated that possibility ahead of time, because this is too stable of a mixture. But that's good. That's a good question, because that's something that we should consider. Sure. Okay, the other possible the other possible mechanism, let's see here, this would be two NOs. Sorry, turn down the volume. These cancel out. Two NOs plus an O2 yields two NO2s. So this checks out. The net reaction is the desired reaction. The other possible guess might be an NO reacting with an O2. If I have an NO and an O2, what could form? NO3? Okay, if I tried to draw the Lewis structure for NO3, get something like this. Nitrogen, I'm overdoing the electrons. Nitrogen is 5, oxygen is 6, so that's 18 plus 5 is 23 electrons. So here I have 24 electrons. I can't have 24 electrons. And so I'm going to go like this. Or maybe oxygen wants it more, so I'll go like this. Okay, so now I have 23 electrons. Now I'll try to complete the octets. I'm going to try to complete the octets by maybe forming double bonds here. But I can't exceed an octet on nitrogen. Nitrogen, that's a law. Nitrogen cannot have more than an octet. And so I end up with something like this. Does this look good to you? No. No. So we're going to eliminate NO3. NO3 minus is good. NO3 minus is good because it has an extra electron to make that octet. And so if we had NO3 minus, but this is NO3 with zero charge, it's not going to happen. Give me something else.
Seems like we need two nitrogens to make
I was like, everything
stable. Because O3 would be pretty good. Ozone, but
Yeah, ozone is good,
it has a free radical.
but it has this free radical nitrogen. Now, What else? I've seen lots. I've seen this. Does this seem reasonable to you, or does that seem absolutely crazy? This is crazy. I mean, this is like 4 free radicals is crazy. That'd be extremely reactive, unstable.
It seems like it's most stable in its current state.
Yeah, right. In its current state seems. I mean, it could form free radicals. You know, that's always a possibility. It could form free radicals, and if we didn't have a choice, then we would form free radical, and we try to form the more stable of the free radicals. But we do have a choice here. If there were no choice, then maybe, yeah, I'd say nitrogen free radical here is possible. Maybe a nitrogen free radical here is possible. But we have a better choice, and that better choice is N2O2. No free radical, everything's got knocked out. And so what we'll say is this is the most likely in terms of energy. Energetically, this seems to be the best. If we didn't have this, then we'd look at which free radical looks the best. Maybe it's hard to tell, so we try all of them. Okay, that's one part of a plausible mechanism. What's the second part of the plausible mechanism? Yeah. Could the first step be the slow step? Could I say step 1's a slow step? No. And the reason I can't is because it wouldn't agree with the experimentally determined rate law. So if the theory doesn't agree with the experiment, then forget it. Could the second step be the slow step? And so that's our only choice is the second step. Okay, the second step I'm going to call K2. And so the rate for the RDS, which is the second step, is equal to K2, and then it's going to be first order at N2O2 and first order in O2. This doesn't agree either. But there's one thing about this second step. And the one thing about this second step is N2O2. N2O2 is an intermediate product. And intermediate products are not allowed in the rate law. Not allowed in rate law. So the way we get rid of that is by doing this. The first step we're going to say is reversible, like this. And so if the first step is reversible, then we're going to have K positive 1 and K negative 1. K positive 1 would be the rate constant in the forward direction. K negative 1 would be the rate constant in the reverse direction. Now, there are 2 ways to get rid of this. The 2 ways to get rid of this are, one, we could use the steady state approximation. Or we could use a simplified version of the steady state approximation. The steady state approximation simplifies into what we call the fast reversible. And so simplified version of the steady state. The fast reversible is valid if K2 is small. If K2 is small, that means the second step is slow. And so what we're going to do is we're going to do the fast reversible because it's easy. So we'll do 2 first, fast reversible. So for step 1, what we say in the fast reversible is the forward rate is equal to the reverse rate. And that is, the forward rate is going to be K1 NO times NO. So we'll just say NO squared. The reverse rate is going to be K minus 1 times N2O2 to the first. And so we're going to say that this first step is in equilibrium here. And so the forward rate is equal to the reverse rate. This is an approximation or simplification of the steady state, because what we're doing is we're assuming that very little N2O2 bleeds off into the second step. That is, most of the N2O2 goes back here. That way we can have this fast reversible. If K2 is big, what happens is that's like a leaky balloon. Let's say this is my balloon. It's happy. The balloon is happy. But if there's a leak, let's say there's a pinhole. If there's a tiny pinhole, it's okay. A little bit of N2O2 leaks out this way in step 2. But if there's a large hole in my balloon, then lots of N2O2 is going to leak out the hole, which would be K2. And so what we're doing is, in the fast reversible, we're ignoring the leakage here. That is, the forward and the reverse are equal. And this is at equilibrium. Okay, if that's the case, then we solve this equation for N2O2. And so we get N2O2 is equal to K1 over K minus 1 times the NO squared. And then what we'll do is we'll substitute that into our rate law. So we'll substitute it back here, and then we'll get our rate is equal to K2, and the N2O2 is going to be K1 over K minus 1 times the NO squared times the O2. Okay, what we're going to do is we're going to combine these into one big constant. We'll just call it K. And then it's going to be NO squared times the O2. So if we get rid of the intermediate and instead represent in terms of reactants, NO in this case, then take a look. Do they match? The mechanism gives this rate law, and the experiment gives the same rate law. So that means that this mechanism is plausible. Now, there could be other mechanisms we just didn't think about, but we won't worry about that. Now, we have a plausible mechanism. Okay, the other scenario is, what if the bleed out here is rapid? What if the N2O2 doesn't all go back? And then just a small amount goes forward here. So if K2 is larger, then we have to account for that. And so let's do the steady state approximation for this. So rather than saying in the fast reversible, we just say step 1, forward rate equals reverse rate. For the steady state, we do this way. In the steady state, what we're going to say is that the for N2O2, the rate of formation or production is equal to the rate of consumption or destruction, whatever we want to call it. And so how do we form N2O2? N2O2 is only formed from K1. And so that's K1 times N2O2. We're saying the first reaction is reversible, the second one is just one way. Okay, what is the consumption? Well, the consumption, N2O2, we can reverse this. That would be K minus 1. So we'll get K minus 1 times the N2O2. Or it would be this one here, the second step. It gets consumed. So in the second step here, where it gets consumed, this would be K2 times the N2O2 times the O2. Okay. So what we'll do is, what will we do here? What we'll do is we'll get this in terms of N2O2. So we'll have to factor out the N2O2 here. And then figure it out. So, etc. Etc. Because, let's see.
Yeah, I would like to know at some point what et cetera is.
Okay.
Even if it's like tomorrow.
No, actually, today's gonna be it. We will do the etc. with a different example. I'll do the etc. with a different example here. Etc. is just solving it for N2O2 and then substituting, which we can do. Or should, maybe we'll just do this one too.
Why isn't the K1 NO squared? Why is it N squared? And
Oh, that's a good question. Because I made a mistake. It's not N2O2. It's K1 is NO squared. You're right. That was a mistake. And so the etc. here is solving for N2O2. And so we'll factor out the N2O2 here. If I factor out the N2O2, I'm going to get K minus 1 plus K2 O2. And then dividing by K minus 1 K2 O2. And so this is going to equal K1 NO squared over K minus 1 plus K2 O2. And then the rate of the RDS is equal to K2 times the N2O2 times the O2 that we had up earlier. And substituting this in here, we're going to get K2, K1 NO squared, K minus 1 plus K2 O2. Here. Times O2. Now, it depends on how big K2 is. If you take a look at this term here, this is K2 times the O2. If K2 is negligible, that is, if K2 is very small, it's a tiny pinhole leak that's occurring in step 2, then this plus this is just equal to this. That is, this is negligible addition to K minus 1. If K minus 1 is big, K2 is small, so tiny pinhole leak. Then what happens is this term drops out. You know, this is the simplifying assumption, basically. And then you see the rate law that we get is exactly the same as fast reversible. So fast reversible happens when K2 is very small. But if K2 is large, then the order is more complex for the reaction. Do you see that? And the kinetics are more complex. So we have to factor that in. And so it depends on the magnitude of K2. So the fast reversible works. It's just as long as K2 is small. How do you know if K2 is small? You don't, unless you have the numbers and you can see. You know, if we could ignore it or we can't. Okay, so that's the fast reversible, and that is, this one yields two. So two possible scenarios here. K2 is small, then the rate is equal to K NO squared, O2. K2 is significant, that is, it's more than a little pinhole leak, then we get this equation here.
Are we assuming that the K1 over the K negative 1 cancels out?
No, it doesn't cancel out.
So how is it being combined with K2?
No, what we're saying is that K2 is so small, so this is like K minus 1 would be like a swimming pool, and K2 would be like a drop in the swimming pool. So it's the simplifying assumption, so that cancels out. Then what we do is we'll just combine the constants. K2, K1 over K minus 1 is just equal to K, the new constant. So we're not really canceling it out. We're just combining it into a new constant. Okay. And so that's what this K is here. It's a combination of all the constants.
So it would be like a different value that we wouldn't
Yes.
necessarily be able to calculate ourselves.
It would be a different value. Here's an application of some kinetics, in smog. So we can see what happens with the species in smog over time. And so if you have photochemical smog, the species changes. Like you have hydrocarbons here, you have nitrogen monoxide, nitrogen dioxide. The nitrogen monoxide concentration drops rapidly because that's converted quickly to nitrogen dioxide. But these concentrations drop off and we end up forming more ozone and PAN, which is peroxyacetyl nitrate. And this PAN is fairly reactive. PAN and ozone. Ozone's fairly reactive too. Ozone's pretty unstable compared to O2. Ozone could undergo unimolecular collision. If ozone collides with the wall, or if ozone collides with the nitrogen, it could break off into O2 and atomic oxygen. In fact, that's what happens, and that atomic oxygen is very reactive and causes irritation. Catalysts provide an alternate mechanism for reaction. And so let's take a look at some catalysts. Those were the two scenarios for mechanisms that we look at. This is what we call a heterogeneous catalyst. So this is the catalytic converter in a car. Carbon monoxide is generated from incomplete combustion of hydrocarbons, gasoline. Nitrogen oxides, or oxides of nitrogen, like nitric oxide or nitrogen monoxide, here is generated from high temperature reaction. I said N2 and O2 are very stable, unless they're subject to extreme temperatures and pressures. When nitrogen and oxygen in air are subject to high temperatures and high pressures, it can form NO. But these are components of smog. And so what we do is we can use a catalytic converter. Catalytic converters have some precious metals, oftentimes like rhodium or platinum. I used to use platinum, but not so much anymore, I think. But still, they're very expensive as these precious metals. And these precious metals have empty d orbitals. These empty d orbitals are thought to be the active sites, where molecules can kind of attach to. That attachment is called adsorption, or adsorption here. And then we have some reaction and then desorption here. Exactly how this occurs isn't really well understood. So people are working at gaining a better understanding of what happens in this type of catalysis. But what's thought to happen is we're going to lower the activation energy here to speed up the reaction by giving it an alternate mechanism. So the alternate mechanism is adsorption here, forms this stable somewhat. And then surface reaction here, we've got to come together and react. And then desorption here. Okay, after they react, the electronic environment changes and they can desorb off the surface. And so we end up forming CO2 and nitrogen, which are much better than CO and O. People are looking, as far as theory goes, people are looking theoretically what would make a better catalyst using less expensive materials. That's one, or the experimental approach is just mixing together different alloys and see which one works the best. Okay, this is a homogeneous catalyst. This is the decomposition of formic acid into CO2 and water. And it has a big activation energy. This happens in one step here. Here's the transition state. So we rearrange electrons to form carbon monoxide and water. But if we have acid, which would be a homogeneous catalyst because the acid is going to be in the same aqueous phase as the formic acid. And so the acid can come in here and catalyze this reaction. And so we can do uncatalyzed versus catalyzed here. Mechanistically, we're going to see that there's going to be a big difference in energy between the catalyzed reaction and the uncatalyzed reaction in terms of activation energies. So in the uncatalyzed reaction, let's take a look here at formic acid. Formic acid has this structure. Formic acid is the simplest of all the carboxylic acids. Like that there. This hydrogen is not your typical hydrogen here. This hydrogen is a lot more acidic than a normal hydrocarbon, hydrogen, because what's the oxidation state on this carbon? +3. Yeah, +3 is kind of high, compared to normal hydrocarbon carbon. Normal hydrocarbon carbons are negative, the electron rich. This is electron poor. It's a +3 oxidation state, which is going to mean that this hydrogen normally is nonpolar. When you have a hydrogen bonded to carbon, it's typically nonpolar, but this is going to make this hydrogen a lot more polar. And so this hydrogen is actually going to have a positive charge build up because this carbon's sucking electron density a lot more than it normally does. And so what that means is this hydrogen is a lot more acidic than a typical hydrocarbon hydrogen. A typical hydrocarbon hydrogen is not acidic at all. This oxygen is delta minus. And so what has to happen is you have to have a vibration, and this vibration is going to push these are sp3 lone pair electrons here. We have a vibration here that pushes these sp3 into the s. And so we'll get sp3s overlap, which can create a bond and kick out these sp3 from the s. So we end up with something like this. At the same time, we have that. We're going to have, what are we going to have? Let's see, we're going to have these electrons break off here. Otherwise, this oxygen is going to gain a positive formal charge because they had 3 bonds in one lone pair. And so what we're going to end up with is something like this. And then we need to make an octet, and so In order to make an octet, we have to have this happen. And so maybe it's going to happen like this. This will be step 1 here, which will set off a cascade of rearrangement. And that cascade of rearrangement is going, this transition state's going to be this rearranging type deal here, and then we're going to end up with carbon monoxide and water. Carbon monoxide is C triple bond O and H2O. Okay. Do you see that? The mechanism? So this intermolecular, that's not inter. Inter is between molecules. This would be an intramolecular proton transfer. Talked about before. Okay, that's for the uncatalyzed reaction. They're calling it in one step here. I might have done it in multiple steps, but it's all right. What about the acid catalyzed reaction? Well, formic acid is an acid, so why would an acid react with an acid? Well, we have to look at it atom by atom. And so even though formic acid is an acid, it has some base sites on there. Base sites would be atoms that could behave as a base. One of these would be this oxygen here. In fact, this oxygen is acting as the base. This hydrogen is acting as the acid. So we already seen this oxygen act as a base. But there's a much easier hydrogen to attack here if there's acid present. If there's acid present, then this one's just an empty s orbital here. And so what can happen here is that this can just latch onto that hydrogen there. If that latches on the hydrogen there, then what forms? Well, what forms is we're going to have this. I could have broken this one up into multiple steps here. But since the book didn't, I'm not. I should have probably broken that up into multiple steps because this is what's going to happen here. But this is going to generate a positive formal charge on that oxygen. And so maybe it's not as happy. So what we're going to do here is this oxygen is going to just take the electrons here from the bond, like that. Okay, so we end up with forming a water and this HCO species here. And so we'll end up forming this HCO and a water. Water is always good. Water's got octets and zero formal charge. But this HCO species isn't so great because this carbon is going to have less than an octet and a positive charge. And so what can happen here is this. In the next rearrangement, we can get this carbon to take the electrons, the bonding electrons here. And that'll reduce its formal charge, but it doesn't have an octet. And so at the same time, we're going to create a triple bond there to generate that octet. And so we're going to end up with this. We're going to end up with a C triple bond O. Carbon monoxide, a water, and the H plus. And so we regenerate the catalyst. So in the first step, we consume the H plus. In the last step, we regenerate the H plus. And so the catalyst participates in the reaction, but it's regenerated at the end. So its concentration doesn't really change, of course, the reaction. And so when we look at the mechanism, these are going to be lower energy transition or intermediate products in this case here. And therefore, the acid catalyzed reaction will speed things up when we rearrange the electrons. All right. Finally, we have this one application from enzyme. Enzymes are biological catalysts. And so they give different names to this thing. The catalyst is called the enzyme here. The enzyme's going to have active sites there. The substrate's the reactant. And so here it's going to speed up the substrate going to products here. Without catalyst, it just goes straight from substrate to products. In other words, it looks like we have to break this bond here. Breaking the bond means that it's going to cost a lot of energy in terms of activation energy. But one way of visualizing the catalyst here is the substrate attaches here, and that could provide some pulling effect. That is this tensile force here that pulls apart on this bond and weakens it. So if the substrate attaches to the enzyme here, it weakens this bond because these active sites are pulling, like in a tug of war, pulling the molecule apart. And if that's the case, then it can break the bond much easier. And so this is showing the substrate, the reactant here, and the enzyme, which is this ribbon structure here. And perhaps in here, there's a little tug of war going on, weakening the bond. Or it could be more complicated. There are different ways that catalysts can work. But anyway, we can break this down into a two-step process. Let's see. The two-step process here is the enzyme plus substrate, step one. And in this one, we could say it's fast reversible. But normally we don't say it's fast reversible here because in enzyme kinetics, step two may be fast or may be slow. And so we're going to use the steady state. And most of the ones that we do in the homework, we would use the fast reversible approximation because this is easier. And then step two is going to be the slow step. And so if the step two is the slow step, then we have the two choices. And we're going to go with the steady state approximation. The steady state approximation is rate of formation is equal to the rate of destruction of the intermediate ES. And the rate of the reaction to form product P is equal to V. V stands for velocity, and that's equal to K2 times ES. ES is an intermediate, we have to get rid of it. We're going to get rid of it by using the steady state approximation, which is shown here. And that is the rate of formation. It's only formed by K1, but it's consumed by K minus 1 and K2. So K minus 1 is a reverse, K2 is a forward here. And so that's what's shown here. They just simplified it. Okay, they did one extra thing here. The one extra thing is this. The total enzyme concentration in this is going to equal the free enzyme, which is given by this term, and the complex enzyme, which is given by this term. And that's the total enzyme. The total enzyme is whatever we dump in there at the beginning of the reaction. So this is the amount of enzyme total that was dumped in at the initial part of the reaction. And whatever we dump in there is going to be either free or complex. And so this is the extra trick to this. I go through this in the Zoom. So I'm not really going to go through the details here, but what we end up with is this very famous equation here. This famous equation is called the Michaelis-Menten equation. The Michaelis-Menten equation depends on the magnitude of the Km here. If Km is very large, or actually probably we don't think in terms of Km, we think in terms of substrate. If the substrate is very small, then it's negligible here, and the substrate drops off. This would be the simplifying assumption. Do you see that? So if the substrate is very small and the enzyme is very large, then we got plenty of enzyme. There's plenty of enzyme for everybody. And so if you're substrate, then you don't have to worry about getting enzyme because there's plenty of enzyme. If there's plenty of enzyme, then it doesn't matter. We'll double the substrate. There's still plenty of enzyme. So if we double the substrate, then we get twice as much reaction. We could triple the substrate. Plenty of enzyme to go around for everybody, triple the rate of reaction. Quadruple the substrate, quadruple the rate of reaction. But pretty soon, if the amount of substrate keeps increasing, eventually the amount of enzyme is going to be depleted. That is, pretty soon there's not going to be enough enzyme for everybody to have an enzyme. People are going to have to start to wait for enzyme until the previous substrate has reacted. Does that make sense? So when you get to higher and higher substrate concentrations, then the amount of enzyme becomes limited. And then it becomes zero order. So for example, a very high substrate, I could double the amount of substrate, but the reaction is not going any faster because there's not enough enzyme to go around for everybody. It depends on the cycle time. The cycle time is how long it takes for the substrate to react. And so this is the classic Michaelis-Menten kinetics. At low substrate, high enzyme, it's first order. At high substrate, low enzyme, the enzyme stays the same, it's zero order. Doesn't matter how much extra enzyme you have, how much substrate you have, you're limited by how much enzyme you have. And so this is the classic Michaelis-Menten. That is, when substrate's small, then it's first order mass. When substrate's large, then the Km term drops out. And what happens? The substrate cancels out, and it becomes zero order in substrate, depends only on how much enzyme. The only way you can fix that is add more enzyme initially. Does that make sense? Okay. And so this pretty much concludes chapter kinetics. So let me stop here. Let's take a break, and then I want to talk about some electrochem.